Okay, so Kevin, what are we going to talk about today?
Um, we're going to be talking about some of the labs this semester. I
Okay,
believe the first one is the calorimetry lab that we're going to
yeah,
discuss right here.
okay. Yeah, so this lab, I'm pretty excited about it because I think that there's really some excellent opportunities for students to be creative. It won't be the first lab that people do. It'll probably be number 4, 5, or 6, depending on what happens. But yeah, I'm pretty keen on it. So in this laboratory, hopefully it relates to things that students are pretty comfortable with and pretty familiar with already, right? I mean, if you make some hot soup or you make some hot tea or a hot coffee or something like that, it's too hot to drink right away, typically, often, almost always is. And so you either wait for it to cool down a little bit, you wait for it to lose a little bit of its energy so that it gets to a temperature where it's more comfortable to drink, or you can add something to it. And the basic premise of the calorimetry lab is you start off with some simulations, and in those simulations, you're looking at learning to calculate the resulting temperature when you add two different amounts of water at 2 different temperatures together. So, and the basis for that is this is the calorimetry lab. Calorimetry. Can you see that all right?
Yep.
And basically, you've got a container. I think they show like a styrofoam coffee cup calorimeter, and it's got a little bit of water in it. And let's say that water is at 80 degrees Celsius, and you've got this other container that has, we'll start off with the exact same amount of water, and it's at 40 degrees Celsius. And it's not rocket science for us to say, hey, look, if I've got two containers of water and one is at 80 and one is at 40, when I mix them together, I'm going to have some temperature that's in between there. And frankly, to the first untrained eye is that the answer should be around 60 degrees when those two are mixed together. In fact, it won't be quite 60 degrees. It'll actually be a little bit less. And that's because all of the energy that's in this 80-degree water is going to get transferred into this container. And it's going to heat up this 40-degree water. But it also has to heat up the container as well. And so when those are mixed, we would say, hey, we know that the amount of energy that is lost by this 80-degree water when they're mixed together is going to equal the amount of heat gained. So Q is the symbol for heat. And so we're going to know that the heat lost by this water is equal to the heat gained by that water. And in the simulation, it's going to teach you that to pay attention not just to the heat gained by the water that's in this cup. So it's going to be the Q gained by the water, but it's also going to be the heat gained and it by the calorimeter. And so when you do that, when you work your way through this, through the simulations, it'll help you to see that, hey, we're going to lose some heat from this 80-degree water. It's going to go into the 40-degree water, but some of it is going to go into the actual walls of this container. And you can probably imagine that a better quality calorimeter will accept less heat and more will go into the water. But that's generally how it's going to be. So that's the first part. You're going to work out, hey, that the heat lost by the water is absorbed by the water of the second container and by the calorimeter. Then once you've kind of gotten comfortable with that, then the task I've set for you is for you to take some hot water that maybe you made turned into coffee. or maybe you bought a coffee. And you're going to either have to figure out or assume what temperature that water is. Chances are it was boiling water. So chances are it was at 100 degrees Celsius. And you're going to take some other water. And this other water, you're going to either figure out that it's room temperature. You're going to look at a thermostat and figure out that it's been sitting around for a while. You might have to let it sit around for a while, but just going to have a defined, known temperature, whatever that is. Maybe it comes out of your refrigerator. Oh, I'm jiggling way too much here. Maybe it comes out of your refrigerator. Maybe it's just been sitting around, but you're going to have to figure out what that temperature is, or make a good assumption of it. And then this hot coffee water, you're going to start taking some water of your colder water and dropping it in here. And you're going to figure out how much of that water you dropped in there. And from that, and this is the part I'm not going to tell you in this video, this is the part that you have to figure out, because you can do this, is you have to figure out, okay, if I know how much water I have here at this temperature, and I know how much water at this temperature I added to it until I could drink it, then you can calculate a final temperature. We call it the drinking temperature. Right? The drinking temperature, which is probably somewhere between these two, but you're going to calculate that, or you're going to experimentally find it and calculate it. So that's what you're looking for. So the first part of the exercise is to teach you some basic calculations between heat lost, heat gained, and and how much it should be gained or lost based on the amounts. And then you're going to figure out a different kind of calculation that will allow you to figure out what the final drinking temperature is. If, as you're doing this, you happen to have your thermometer, you are welcome to use it. But I want you to show me how you did this procedure in such a way that how you did this procedure in such a way that you could have calculated the temperature. So you're allowed to check, if you have access to a thermometer, you're allowed to check it and work it out as you go along. I don't really care what the temperature is. What I care about is that you can design a procedure that will allow you to do that.
Yep. It's really just understanding the concept and trying to figure it out on your own.
Yeah. Yeah.
That's why we're not telling you or what we think it might be.
Yeah. So, Kevin, what do you think of that?
I think that's one of the goals you have listed on the labs. Did you want to explain if you have like a thermos or something? Sure. Yeah. So, so in the next part of it, you could, once you figure out what your favorite drinking temperature is, then you could say, okay, how long does it take for my coffee at 100 degrees to get down to this temperature, right? How efficient, how fast, like if you have it in a travel mug, if you have your coffee in a travel mug, you know it's going to stay hot for a long time. It doesn't say hot forever, right? So maybe you can figure out some way of measuring some time. How long does it take for something to cool down inside your coffee mug? Or if you're using a travel mug, or maybe you're using a koozie on some other, I just want you to take one of those devices and I want you to figure out how long does it take for it to get to the temperature you're at, and then some argument about what the thermal efficiency of your travel mug is, something like that. How does that sound? Yeah, so just kind of, most students are probably going to use like how long it takes for it to cool, and if it takes longer to cool, then it's probably good at keeping heat in, right?
Right. Yeah.
So if you have a thermometer, like you said, you can probably measure out the temperature, maybe be a bit more accurate, but it's really just kind of applying it to everyday life, this concept.
Yeah, it's entirely that, yeah. Is there anything that we've left out that we need to put in this, do you think?
I think we could explain some of the peer review, what you're kind of looking for, because I know
Right.
some of the questions.
Yeah, so on the ones that require a lab report, like the clearly not in the lab manual labs, right? Ones that require a lab report. I want, one of the best things about science is that we don't make progress without being able to show our work to somebody else, and they can either understand it or they can disagree with it, or they can make it suggest improvements. And so for these reserve at home special labs, I want you to share your work once you get close to being to the end of it with some other group, and they'll read through it, and maybe they'll have a couple suggestions. Maybe they'll have something that they don't understand, or maybe they'll be able to say, hey, I like the way you did this, but we did it this way, which is slightly different, right? And or maybe they'll be able to make a suggestion about how you can improve your efficiency, right? Or I'm not sure what they're gonna say, but I definitely want you to share your work with one other group, and probably they will share theirs with yours, and get some feedback that way.
Yeah, I think, like you said, science doesn't really progress with one person. It's a community effort. So
yeah.
A lot of the lab reports in the lab manual, unfortunately, are just kind of, there are some where you share class results, but other ones don't necessarily do that. So
yeah,
this is an example of or it's like a good simulation of real science, kind of.
Yeah, and take it for what it's worth. I mean, there are things that you will learn, right? If you listen with an open heart to what somebody says to you, you can learn things, right? And yeah, so that's what the point of that is.
Yep, I don't think I have anything else to add for the calorimetry lab. I think we covered everything.
All right, well, great to talk to you today then, Kevin. Thank you.
Yep, thank you, Dr. Hunter.